All right, so in today's video, we're going to actually look at the equations of these exponential growth and decay models that you were exploring in that Desmos activity. And I'm going to go back to those two examples of the penny and the March Madness, and we'll talk about writing those equations. And then we're also going to talk about writing equations if something increases or decreases by a fixed percent, because that's also exponential growth or decay. So here is your exponential growth and decay equation. Y equals A times B to the x power. So what you can see is that what's different about these equations that we've done before is our x is now in the exponent of your equation. So if we kind of break this equation down, the y value, or your output, is like your final amount. The A value is your initial amount, so whatever you're starting with. The B value is what we call our growth or decay factor. So that could be like if something doubles or triples or increases by a certain percent, that B value is like how are these values increasing or decreasing by? And the time is your X value. Right? So whatever you plug in for X is going to represent the time that your situation is increasing or decreasing by. So the difference between growth and decay, if your B value, so this B value right here, if that's bigger than 1, then you have exponential growth. All right, so for example, maybe you have something like y equals 3 times 1.7 to the x. That would be an example of growth because 1.7 is bigger than 1. Okay? Now, if the B value is between 0 and 1, so we're not talking about negatives, we're just saying, okay, is it somewhere between 0 and 1, then it's exponential decay. So an example of a decay might be something like y equals 5 times 2/3 to the x, okay, because this factor right here, which is what we call the decay factor, that's 2/3. We're always multiplying by a value less than 1, so we're always going to be getting out a smaller value each time. That's why this is decay. So if you're multiplying by something bigger than 1, your values will increase each time. If you're multiplying by a value less than 1, your values will decrease each time. So that's your difference between growth and decay equations. All right. So let's look at writing the equations for these examples that you did in your Desmos activity. Okay. So the first activity, we had a penny that doubled in value every day for a month. Okay. Well, if I use this model, okay, to write the equation, I'm going to have y equals, right? A is my initial amount. Well, I started with a penny, so there's my initial amount. The B value was the growth or decay factor. So in our case, our penny doubled every day for a month. So that's my growth factor. So here's my equation for the penny problem. Y equals 0.01 times 2 to the x, because what was happening with our money is it was doubling every day. And the x in this case represents days. So I had you fill in a table and tell me, okay, well, how much money did you have after 10 days? Well, if we don't have a table, or maybe I wanted to say, okay, what happens if I take it further than a month? I can use this equation, and instead of plugging values into a table and doubling it every day, I can plug these values in for my time, which is x. Right? So if I want to know, okay, well, how much money am I going to have after 10 days? I'm going to plug 10 into this equation. All right, so if you have your calculators, you're going to want to use these. Right, so I can just type in 0.01 times 2 to the 10th power. Okay, so at the end of 10 days, I have $10.24. All right. Okay, and where this is helpful, right, like, if I want to know, okay, well, how much did I have at the end of the month? 0.01 times 2 to the 30th, we were looking at what happens at the end of 30 days, okay? There I can automatically get out that value that I had at the end of 30 days without having to fill in a big, long table, okay? All right? So again, in your equation, this first value is your initial amount. This value here is like your growth or decay factor, all right? If we look at our March Madness basketball tournament, right, we started with 64 teams and only the winners moved on. So if you remember, we talked about what happens to those 64 teams at the start. Well, after each round, each team is cut in half. So if I were to write an equation for the March Madness basketball tournament, my equation would be y equals 64, because that's what I start with, times 1/2 to the x, because after each round, half are being eliminated, right? So 64 times 1/2, because every time we were multiplying the previous amount of teams by a half. And in our case, x, which is a time, is really represented by rounds here. So if, I think in the table, after I had you fill out the table, I said, okay, well, how many teams are left after 3 rounds? Well, if you don't have a table, we can now take 3 and plug it in for x, right? Because our time here is rounds. So y equals 64 times 1/2 to the 3rd power. That's going to tell me how many teams are left after 3 rounds. So again, you can just type that in, 64 times 1/2 to the 3rd power. I get 8. So after 3 rounds, there's 8 teams left. Okay, so those are your equations for the examples that you did. And you want to follow this equation for any examples that we talk about, doubling, tripling, cutting something in half, things like that. But exponential growth and decay can also be related to percents. Okay, so if we increase or decrease a value by a certain fixed percent, that also is going to create an exponential growth or decay problem, right? So in this case, we just have to fix one or tweak one little thing about our formula from the page before. Okay, so I have 2 different formulas for growth and decay. They're both y equals, where y is your final amount, just like on the page before. A is still the initial amount. The only thing that changes here is instead of it just being b to the x power, like some number to the x power, we have to make that number. So if it's exponential growth, you are going to take 1 plus the rate, which is a percent expressed as a decimal, to the x power, which is still time, okay? Decay, it's going to be 1 minus the rate that your values are decreasing at, and that r has to also be expressed as a decimal. All right, so let's look at 2 examples of growth and decay where we're using percents with this formula. All right, so I picked this one. This is one of the ones you should have picked, or hopefully you picked on the Desmos activity, where the last slide where you had to kind of pick like which ones were exponential growth and which ones weren't. So you had a mixture of some that maybe were linear and you had some that were exponential. So this one was an example of exponential. You drink coffee with 120 milligrams of caffeine in it, and every hour the amount of caffeine in your system decreases by 12%. Okay, so after every hour we're going to be taking away 12% of what was in your system the previous hour. Now that number that's subtracting away isn't the same, but if you think about it, you're always multiplying by 12% each time and subtracting that, okay? So if I wanted to make an equation that modeled this situation, okay, well, the amount of caffeine in my system is decreasing, so this is a decay problem, okay? So I'm going to have y equals A, which is the initial amount. All right, so I'm starting with 120 milligrams of caffeine in my system, times 1 minus R, which is your rate, okay? But the rate has to be expressed as a decimal. So 12% as a decimal, right, that's 12 divided by 100, or if you think about it, remember you put your decimal point at the end, and if you divide by 100, it moves over 2 spaces, so 0.12 is your decimal for 12%. So this is 1 minus 0.12 to the x, and x is time. So if I kind of wanted to clean this up a little, because you're probably not going to get an equation that looks like this, your equation would look like 120 times, well, 1 minus 0.12 is 0.88 to the x. So this is the equation that represents this situation. And if you think about it, this is what is really happening? You're starting with 120 milligrams of caffeine in your system. It's decreasing 12%, so doesn't that mean you're only keeping 88% of the caffeine in your system each hour, right? 100%, think of it like that, minus 12% is 88%. So I have 120 milligrams of caffeine in my system, but every hour, only 88% of that is left. Okay, so this equation models this exponential decay problem. Okay, so if I wanted to know, okay, well, how much caffeine is left in your system after 4.5 hours? Well, the time is x. So if x equals 4.5, okay, I am going to plug in 4.5 for x. All right, and then you can just type this in your calculator. 120 times 0.88 to the 4.5 gives me about 67.5, and we're talking about milligrams of caffeine. All right, so after 4.5 hours, you have about 67.5 milligrams of caffeine left in your system. Okay, if I look at my next example, right, the population of Westchester can be modeled by the equation P equals 19,343 times 1.0136 to the T, where T is the number of years since 2016. So if I said, what's the population in 2016? All right, I'm going to use this equation. Well, this equation is talking about the years since 2016. So if I said, what's the population in 2016? That's like asking, what's this initial value? And our initial value is that A value. Okay, and in our equation, the A value is 19,343. Okay, so if I ever want to know what's an initial value, you're looking at that A value right there, all right? Now this one's tricky. By what percent is the population increasing? So I'm going to look at this value in here. Okay, this value in here, this growth factor is 1.0136. Okay, but remember, to get that number, I did 1 plus some rate as a decimal. So if I break this down, this is really 1 plus 0.0136. Okay, so this value right here, that is really your rate. That's what we're looking for. But this rate is expressed as a decimal. So I want to make this rate go back to a percent. So if I have 0.0136, okay, well, in the problem above, to make my decimal a percent, remember I moved the decimal to the left 2 places, or I divided by 100. If I want to make this decimal become a percent, I'm going to do the opposite. So I'm going to multiply by 100, or what that does is that just moves your decimal place over 2 places, and I get 1.36. So this is the percent increase of the population of Westchester. It's increasing by 1.36%. In your equation, it didn't look like that, so you had to break it up and say, okay, well, that's really 1 plus this decimal. Then take your decimal and convert it back to a percent. Okay, so right now we have a population of 19,343 people. It's increasing at 1.36% per year. So if I want to know what is the current population today, well, I have my equation. P equals 19343 times 1.0136. I need to figure out, what am I going to plug in for the time? Well, the current population today, well, today is the year 2020. But I don't want to plug in 2020, because what that would mean is that 2020 years have passed since 2016. Well, the amount of years that have passed since 2016 to 2020 is 4. So I'm going to plug in x equals 4, or t in this case, t equals 4, because 4 years have passed from 2016 to 2020. All right, so just be careful for asking, a value to plug in. Don't always assume it's the value that they're talking about. You might have to kind of think about what time increment you're talking about and how many years or hours or days have actually passed. And then I can just type this in, 19343 times 1.0136 all to the fourth power. And we're looking at today's population of being about, I can round this to the nearest person, 20,417 people. Okay, so that's kind of what we expect maybe the population of Westchester to be today. All right, so you want to use these formulas if you are doing exponential growth or decay by a fixed percent. So as soon as you see your problem has a percent, you want to follow these formulas. If your problem is talking about doubling, tripling, cutting something in half, you can just go right to this formula where your B value is that actual growth or decay factor, right? So just keep in mind there's a difference between percents and if something's just doubling, tripling, or so on, okay? So after this, you want to watch this short video about the coronavirus because the coronavirus or any virus is a prime example of an exponential growth model where one person could infect a couple more, those people might infect a couple more. So I just included a short video to kind of explain, our current situation and what's going on with that and how that relates to exponential equations since this is the current unit of study.